with me, or are you? Oh, no, it's not. Okay, wonderful. So good morning, everybody, in person and via Zoom. This is, the mic is here. Can people hear me well? Yeah, very good, very good. So this is, I mean, all of you here know me in the room, but maybe some people in the Zoom don't know me necessarily. So I am Ana Navas. I am the director of the Columbia Northern Plains Superfund Research Program. And this event, we are organizing it as part of the center together with some of the entities of the center that are the DMAC, the Data Analysis and Management Core, as well as the training, the RTCC, which is the research and training component for the center. And we have a special session, and it's a real pleasure to have Arce Domingo Reyoso, who is an associate research scientist in the Department of Biostatistics and a member of the center. She's working with Jeff Goldsmith, who is the director of the DMAC, and Arce is one of the key members of the DMAC, of the Data Analysis and Management Core. We were discussing, and one day Arce mentioned that this thing that so many people, all of us, in the work we do, looking at longitudinal data is really essential. In our center, we are looking at trends over time, how those trends over time in very critical exposures for our communities could impact the health outcomes. And looking at trends and longitudinal data is essential in environmental health. And no matter the work that we do, but very particularly for our center. And Arce mentioned so many of us have questions. This is a very complicated kind of topic, and doing one-on-one is not so efficient. And so let's do a panel and bring everybody together. So we are really excited with this session, and thank you so much, Arce, for doing this.
Great, thank you so much, Anna, for the introduction, and thank you all for being here. Also, to those on Zoom, it's great that many people are interested in clustered and longitudinal data analysis. So this is going to be sort of introductory and basic workshop. It's not going to be like high level with complex mathematical models or statistical models. I just want to give you guys an overview on how to analyze this kind of data. I know that, as Anna mentioned, many people are working or have longitudinal data, and sometimes it's not very straightforward to look at how to analyze them properly. So we're just going to give an overview. We are going to go through a practical example through the class while I explain the statistical models. Hopefully you were able to download the dataset and the code. But even if you don't want to code right now, of course, you're welcome to the workshop, because I'm also going to talk about, general things regarding longitudinal and cluster data analysis and why we should be using specific models for this purpose. So even if you don't feel like coding right now, this session will probably be useful. And if you want to code it with me, then that's also great. So I'm going to get started in the interest of time. And this is the outline for today. I'm going to go through the motivation first for cluster data analysis. Then I'll do an introduction to statistical methods for cluster data. So there are many statistical methods that can be used, but these are the two most popular ones. So generalized estimating equations, or GEE, and mixed effects models. Probably many of you are here hoping to be able to understand whether it's better to use GEE or mixed models. Well, I have to give you the bad news that there's no straightforward answer to that. So because, each of them has its own particular features, but hopefully you'll be able to understand them a bit better and choose which ones to use depending on the situation. And then we'll also go through some final remarks that are also relevant. So let me start with the motivation for cluster data analysis. Of course, feel free to stop me anytime with questions, because that's what we're here for. And also those on Zoom, hopefully I can hear you, or Whitney can tell me if there are questions. So a clustering factor refers to a common factor that induces correlations between individuals. So one example might be patients within different hospitals. So these patients from a given hospital might share some common features, such as treatment strategies of the doctors. So these might induce some correlation. This is an example of some cluster data. Another example might be gene expression measurements across batches. So for omic data, measurements that are taken in the same plate, in the same chip, in the same batch, might have some correlations due to the way they are measured. So we need to take care about that unwanted correlation that might be present in our data. And then the most obvious example, and the reason why probably most of you are here today, is as this specific case of cluster data, repeated measures of some clinical marker over time. So this is the case of longitudinal data. And this is a special case of cluster data because here, if you realize the grouping, the clustering structure is the individual, because we have repeated measures over time for the same individual. So here we consider the clustering structure, the individual itself, and each person represents one separate cluster. So the question here obviously is, can we just take this data and analyze them all together using, for example, linear models? Well, obviously, you all know that the answer is no, otherwise you wouldn't be sitting here today. But can anyone tell me why can't we just take this data and analyze them all together? What is it that makes it incorrect to use, like, for example, a linear model to analyze this data? Any idea? No? Okay. So the reason is that these data are not independent, right? So most of the regression models rely on the independent assumption. So they consider that basically the data set we are providing is composed of samples, independent samples of a population. And the assumptions, the statistical assumptions won't hold anymore if those data are not independent. So this means that in addition to the parameters we want to estimate from our models, we need to take care from one additional parameter, which is the correlation. So there's another reason why we would want to use specific models for this purpose, in addition to being incorrect to analyze this correlated data with regular, for example, linear models. These specific models for cluster data enable obtaining some interesting information that you wouldn't be able to obtain with, for example, regular linear models. So you're able, for example, to obtain the association between an exposure and the change of an outcome over time, which is something you cannot obtain in principle from a regular linear model. So that's another reason why you will want to use these models. So in practice, we typically assume two things. We assume study units between clusters to be independent. So the observed cluster, each observed cluster, is a random independent sample from some population of such clusters. So we have a population of clusters, and then the population that we have is composed of some independent samples from those clusters. But then there's another level. There's the individual level within the cluster. So we also assume some structure of dependence within clusters. So there are two levels that we need to take care of, and that's why some of the most popular models used for this purpose are called multi-level models. Now, another question that rises a lot in this context is adjusting for confounding the same as clustering? What's the difference between those two things? Do you think adjusting for confounding and clustering are the same thing? No, right? Adjusting for confounding is different from accounting for clustering. So why? First of all, in terms of definition, let's go through these two concepts. Confounding, a confounder refers to a variable that influences both the exposure and the outcome. And most of you here probably have taken AP classes, so you know this better than I do. But that's the definition of a confounder. Whereas a clustering factor refers to a grouping factor that induces correlations between individuals. So the definition is different. But what about the purpose? The purpose of adjusting for confounding is actually to remove bias caused by a confounding factor. Whereas the purpose of clustering, of accounting for clustering, is to account for the dependence between observations. There are also differences in terms of the methods we use. In fact, confounding, adjusting for confounding is much more simpler. So for confounding, as you probably all know, we just adjust the statistical models for the confounders. There are also some other methods that can be used to account for confounding. I mean, more sophisticated methods, but generally adjusting is what people tend to do. So for clustering instead, we have to adjust this for the structure of the data. So using, for example, multi-level models. So I think we would all agree that confounding is a simpler approach than clustering. But in terms of examples, we can clearly see here, for example, age is a very typical confounder for many associations between clinical markers and health outcomes. So we wouldn't consider that a cluster, right? That's a confounder. Whereas, for example, repeated measures on the same individuals, that's a clustering structure. So we wouldn't consider it a confounder. Now, is it that clear always, the difference? No. There are some clustering factors that might also be confounding your associations with your data. So sometimes it's not very easy to differentiate these two. So my advice would be to fit both models to, in case you're not sure about this, you can adjust for confounding and you can consider that as a grouping, as a clustering structure, and compare the results. Obviously, if the results are very similar, then you should always go for the simplest model. Because in statistics, right, if our data can be represented by a simpler model, then you should always go for that simple model. Then if the results are different, then you will need to guide your decision and also the scientific context you're looking at. So let's go through a practical example that we're gonna go through in the whole workshop. Basically, this data set that I sent you all has 26 children that were followed at the UNC Dental School in the 60s. And we had a total of 104 visits. So each children was followed every 2 years from 8 to 14 years of age. And the main outcome that we're interested in is the distance between pituitary gland and pterygomaxillary tissue. So we can see in the picture that's that distance. So if you were able to load the data, you can do a head here and look at how the data looks like. So basically we can see that we have the ID repeated 4 times because we have 4 measurements for that individual at different ages. So you can see that the age variable is increasing and we have different lengths for each age. So the gender variable is obviously constant across all the measurements. And then we can also look at the number of rows, which is the total number of measurements. It's 104, as I mentioned, but there are only 26 unique children, unique IDs in this data. So we can plot our trajectories. We can do what's called a spaghetti plot of the trajectories. And here I'm using the ggplot2 library, which is very helpful to make nice plots in R. And we can see that there is a trend in dental growth. There is an increasing trend, and it looks like it might be different for female and for male, right? Because the red ones are males and the blue ones are female. So there are some oscillations, but we will see what we can get from this data. So let's start with the statistical methods that can be used for cluster data. Again, there are many statistical methods that have been implemented for this purpose, but the most basic ones and the most widely used ones are generalized estimating equations and mixed effects models. So let's go through each of them in a little bit of detail. And I'm going to start with generalized estimating equations, or GEE. So basically, GEE is an extension of the generalized linear model to cluster data. And the key feature here is that it's a marginal model, in the sense that it's a model of the mean of the outcome. So it cannot make individual predictions. It provides a mean across all clusters. So that's a marginal model. And keep this in mind because that's different for mixed effects models. So it uses the weighted least squares method. And basically, this is a modification of ordinary least squares, which are the ones that are used, for example, for linear regression. So it uses the correlations that we can observe in the data across observations as inverse weights. So this means that if the outcome is continuous and no correlation within responses is assumed, then it's equivalent to ordinary least squares, because we will be supplying no correlation between structures. So that would mean an equivalent model to ordinary least squares. Whereas if our correlation structure is more complex, then that's adjusted using the weights. But since those weights depend on our correlation, we need to place some structure on the covariance in order to help the model obtain valid confidence intervals. However, a very attractive feature of the GEE model is that even if we supply a wrong working correlation structure, because we were not sure or we're just wrong about the correlation structure, that we can still obtain valid inference because of one very popular method, which is the robust sandwich estimator. So this method is able to obtain robust standard errors, even if our correlation structure is wrong. So let's look at the correlation structures. Again, even if we are able to obtain valid inference, if we are wrong about the correlation structure, we might as well try to be right about the correlation structure, because this helps the model. This helps the algorithm be more efficient and estimate the standard errors given our information in the data, right? So there are 5 different correlation structures that we might be able to use. And the most popular one, at least for longitudinal models, is the exchangeable correlation structure. So this structure assumes that there's equal correlation between individuals in the same cluster, right? So that's a reasonable assumption. And again, this is very popular for longitudinal data. So another choice that could be possible is the independence correlation structure. So this assumes that there's no correlation within individuals in the same cluster. And you might think like, why would you choose this correlation structure? If you assume there's no correlation between individuals, you might as well fit just a linear model, right? Because we're just about correlations in here. Well, the reason is that there are some papers out that show that if you're not sure about the correlation structure, for example, specifying an unstructured correlation structure might be less efficient than an independent one, because you introduce more noise in the model. And also in some particular settings, like with time varying confounders and so on, there are some papers showing that you might get biased results if the correlation structure is wrong, except if you specify an independence correlation structure. So basically, this could be used if you're not sure, or if you think you have complex correlation structures. Then another popular one is the AR1 structure. This is basically a correlation decaying as a function of time. So we're, for example, assuming that measurements that were taken far apart in time are less correlated than the ones that were taken closer in time. So this could be useful, of course, in the setting of longitudinal data if they show a trend. Now, another choice is the unstructured one. So this is not really recommended unless you have strong reasons to use it. And the reason is that this allows the correlations to vary totally freely. So this is obviously very inefficient because you're not providing any information to the model. You're just allowing everything to vary freely. So you're not really making any constraints. You're not making the algorithm more efficient with this unstructured correlation. And then you can also provide a user-defined matrix, which is just if you know the correlation structure in your data, which is not that common, but will happen, you can just provide your own correlation structure. So some considerations here, again, important. You can obtain consistent estimation even if the specified working correlation does not correspond to the true underlying correlation model. So the sandwich estimator for robust standard errors will take care of this. So an important thing here is that you can obtain from the GEE model these robust standard errors and also the standard errors that were fitted using your correlation structure, right? So if those two standard errors are very similar, then that means you did a good job specifying the correlation structure. Because then the sandwich estimator is providing the same standard errors as the ones that were fitted using as weights the correlation structure that you provided. So that's a way of looking at how confident you are about your correlation structure. Now, another key point here is that GEE methods are not based on likelihood, right? It's a totally different estimating procedure, and therefore criteria like AIC, BIC, log likelihood, which are generally used to select the best model among nested models, these are not going to work here for GEE. So there is one modified procedure, which is called the quasi-likelihood information criteria, QIC, which people tend to use to select, for example, the best correlation structure between two models. And of course, this works just like the AIC in terms of the smallest one should be the best. However, some caution needs to be taken here because this QIC, some experts have warned about it having some problems in terms of not being the best way to select between models, because again, this is not based on likelihood. So some experts advise using just the scientific context to select the correlation structure instead of looking at QIC. So people still use it, but just be cautious about how much you rely on this measure. All right, so let's go back to our data example of the dental growth curve. We're going to try to analyze this data using GEE. So there are two packages, at least, in R that you can use to fit GEE models. One is the GEE, and the other one is GEE pack. So they are equivalent essentially, but the GEE GLM function from the GEE pack provides also p-values, which are not provided directly from the GEE, so you have to calculate them. So it's easier just to use the GEE GLM. But again, they are mostly equivalent. And here we can see that we have an interaction term in our model. So the reason for that interaction is that we are interested, for example, here on the association between gender and the longitudinal change in length or in dental growth, right? So we are interested in estimating how that association varies over time. And here our time variable is age, right? Because measurements for children were taken in different ages. So age is our time variable here. So with the interaction term, we are basically looking at how the association between gender and length varies over time. So that's what we are actually interested in GE or in longitudinal models. That's why we include this interaction term, and we will see how to interpret it. Again, here we have to specify a correlation structure. So I chose exchangeable because this is a longitudinal model. We assume equal correlations across each cluster. So let's look at the coefficients here. We have first this coefficient of gender male, this minus 1.07. Anyone knows what this coefficient means? What's the interpretation of this concrete coefficient? No? So the interpretation is the mean difference in length comparing men to women at baseline. Why at baseline? Because here, this is an interaction model. So if we are only looking at the coefficient of the gender male without taking into account the other interaction term, then that means that we are in time zero because we are ignoring the coefficient of the interaction. So this refers to baseline. The next coefficient that we have is the age coefficient. So the interpretation of this is just the mean growth in 1 year. Here we're not taking into account gender because it's only the coefficient of age. So that's just the mean growth. Now there is another value that we are interested in, and it's actually the one that we're more interested in this model, which is the sum between these two coefficients. The coefficient for gender and the coefficient for the interaction. Why is that? This represents the longitudinal change in length comparing men to women for 1 year increase in age. So this is actually the association with the trajectory, which is the ultimate reason why we are using these longitudinal models and the quantity we're most interested in. So the association with the trend, with the trajectory. So why do we have to sum the coefficient of gender and the coefficient of the interaction? What's the reason behind that? Let's look at this. This is one of the just two equations that I have in the whole workshop, promise. But it's very helpful to look at this because this is our regression model, and we have a coefficient for gender and another one for the interaction. So this means that gender is present in those two coefficients. So we need to add them if we are to make an inference about the longitudinal change. All right, so we went through the GEE model, and then a different approach to analyze longitudinal data. Oh, I see there are some questions. Whitney, can you, I'm not sure if I can access Zoom in here, but. So there are some questions, I think, in the chat.
No.
Oh, okay. Okay, great. Because I saw like two. Okay, perfect. All right, so let's look at mixed effects models now. Basically, mixed effects models are multi-level models that contain both fixed and random effects. And we're gonna see what this represents in a minute. But basically, importantly, these are conditional models, unlike the GEE model. So they model the mean difference when holding the cluster invariant constant. So conditioning on clusters. So GEE was providing us the mean of the population. This is providing us the mean conditional to the clusters. So that's the difference in the interpretation. But as I said, there are two parts here. There's a fixed effects part and a random effects part. The fixed effects refer to the effects that are common to all clusters, whereas the random effects are specific to clusters. So they allow cluster-specific perturbations, and that way they model the correlation among the study units within a cluster. So that's the difference between the fixed and the random effects. And we can actually see it in this equation, that this first part is similar to a regular, linear regression equation that you've seen, like the X is the covariates and the beta are the effects. But now we have some additional parameters to take care of, which are the random effects. So this linear mixed effects model is similar to the structure of linear models. It just has an additional layer of complexity. Now, we have both fixed and random effects, and in random effects, we also can have random intercepts and random slopes. So let's look at the difference between these. We can see in this plot, on the top right part, we have a model with random intercept and a fixed slope. So basically, you can see that each individual has a different starting point, but the slope, so the trajectory, the growth, is the same for all individuals, right? Whereas if we look at the bottom left, we can see a situation in which all individuals have the same starting point, but then their weight, the slope, is different for each of them. So the growth, the trajectory is different. And then we could have both. Random effects, having random intercepts and random slopes. So these would refer to the setting in which, again, each individual has a different starting point, but then also the trajectories are different, and they could even be in opposite directions in some settings. So those refer to random intercepts and random slopes. However, keep in mind that random slopes should generally only be used if you have multiple measurements, because otherwise it's very difficult to estimate a trajectory of the association, a slope. If you have only two measurements, then that's not going to be enough to look at the changes in slope generally. So my general advice would be that you fit a model with random slopes only if you have multiple time points, not just two. So mixed effect models are based in maximum likelihood, unlike GEE. And maximum likelihood sometimes exhibits small sample bias, which means that results could be biased in settings in which the sample sizes are small. So that's why this modified maximum likelihood, restricted maximum likelihood, is sometimes used to estimate the variance in settings of small samples. So if the sample size is sufficiently big, then maximum likelihood and restricted maximum likelihood should be equivalent. So restricted maximum likelihood is included as an option in most of the mixed effect methods in R. For example, actually, for many of them, it's the default choice of the model. So this is a very important key point, which is that for continuous outcomes, a linear mixed effects model with a random intercept should be equivalent to an exchangeable correlation structure in DEE. That's not always the case, but it should be equivalent, at least for point estimates. So that's the equivalence we have between the two models. Again, only for linear models. And the interclass correlation coefficient is actually an indicator for how much group-specific information is available. So this can tell us whether we should use a random effect or not. So is there sufficient variability between groups to take the risk, I guess, of considering a more complex model using random effects? Or is there really not that much variability and we don't need a random effect? So you can evaluate that using the ICC. All right, so let's go back once again to our practical example of the dental growth curve. We're gonna try to feed now a model, a linear mixed effects model, to this data to see how it differs from T. So again, there are a couple R packages that you can use to feed linear mixed effects models. LME4 is one, and LME is the other one. So they are kind of similar. It's just as LMER, that function, I think it allows for nested clustering structures, and it's more difficult to specify with LME. But again, if you just have random intercepts, random slopes, you can use any of these methods. And here we again have the interaction term that I was talking about in GEE. But I also have this, which is a random effect. So this one is telling us that this is a random intercept. It's not a random slope. And we are treating as random effects the individuals. Because again, as I mentioned before, here the individual is our grouping structure, because we have several measurements for each individual. So individuals are our grouping structure, and we're fitting this model with a random intercept. So let's look at the output of the model. First of all, linear mixed effects model fit by REML. So again, this model by default is using restricted maximal likelihood. And this is providing AIC, BIC, and log likelihood. That's because this is based on likelihood. Again, mixed effects models are based on likelihood. So you can actually use AIC and these kind of measures to compare nested models. And again, the smallest AIC would be the best one. However, it would be advised to use maximum likelihood instead of restricted maximum likelihood for model selection. And the reason is that when the fixed effects are not the same, restricted maximum likelihood takes care of additional degrees of freedom due to random effects. So the models might not be totally comparable. So even if for estimation, it's better to use restricted maximum likelihood, especially if you have small sample sizes. For model selection, it might be better to use maximum likelihood. So you can just change that option in the model. But looking at the fixed effects coefficients we're interested in, again, this first coefficient is providing us the mean difference in length comparing men to women at baseline. And if you recall, this is exactly the same result of the coefficient that we got from GEE. Now, again, the next one is the coefficient of age. So this represents the mean growth in 1 year, just exactly as the GEE model with the same value. And again, we are also interested in this sum, which is the longitudinal change in length, comparing men to women for one increase in age. Yes, Will.
Would there be an interpretation in adding the estimate for age and then the interaction with gender and age?
Separately, you mean?
Like, if we added the value for age and then the value for the interaction between gender and age, is there an interpretation for that?
So, I mean, since age is your time variable, you will be you would be interpreting the longitudinal change in length. So, for example, for the age coefficient, it's the mean growth in 1 year for the reference value, because you're not taking into account gender there. So if you're interpreting the coefficient of age, you're assuming that you're interpreting that for the reference value, which is the female here. Whereas if you add the coefficient of the interaction, then you're also bringing gender into the equation. So it's not for the reference value anymore, because age is part of the interaction as well, right? So basically, it's like as if you got 0 and 1. So if you have the reference value for the coefficient of age, then you will have a 0 in the value of gender. So that means that the interaction doesn't play a role, right?
Okay.
So then if you don't have that, then the interaction plays a role, so you're also considering gender. So that's the key. That's why it gets a little tricky if you have several interactions or like multiple ways of interaction. That's a bit trickier to interpret.
How do you get ICC?
Oh, ICC, it's actually in the model. So you can get it from the model itself. There's a function that if you, I think it's ICC actually, the function. If you do ICC of the fit or something similar, it gives you the interclass correlation coefficient.
Great, thank you.
Is there something in the chat? No. It's like,
How about standard error? Should we also add? And there's another question saying, is there an R notebook available or a GitHub repository with sample coding to get us started?
with sample code of?
Are you gonna be able to make this code available?
Oh, of course, yeah. Yeah, I will share the slides, and I didn't do any GitHub repository, but that's a good idea, actually. But yeah, definitely I will. I mean, I shared the code already, but I'll share the slides for the interpretation and everything. And of course, I'm available for any questions you have via email as well.
And then how about standard error? Should we
Yeah.
also add?
So that's a good question. So the standard errors, you should also add them, but if you're gonna do a different time scale, if you wanna look at a different time scale, so for example, in longitudinal models, instead of 1 year increase, you might be interested in a 10 years increase or in 30 years increase. So that's a little bit more complicated because you need to do some transformations of the variance covariance matrix, taking into account that you are modifying that time variable. So the easiest thing here is to transform the time variable you're using before fitting the model, and then fit a different model for that. So for example, if you're interested in a 10-year increase, the association of, the longitudinal change in 10 years, you could divide your time variable by 10 and fit a new model. So that's going to give you the interpretation in 10 years. But for this model concretely, which is just 1 year increase, since you're not like doing any transformation in the time variable, then it's fine to add the standard. Okay, so as you can see, these results were, just very, very similar to the ones we obtained from GEE. But let's try to fit a model with random intercepts and random slopes. So here we can again see the interaction term, but we can see that here we have age. So that one that was there is not there anymore. So that means that we're not talking about only random intercepts, but also random slopes. So we're allowing each clustering unit, each individual, to have a different trajectory, a different association with the trajectory, which might be the case, in longitudinal models sometimes. But again, this adds an additional layer of complexity. So just make sure that you really need those random slopes. I mean, you can compare the models with and without random slopes to see if that's worth it or not. So looking at the coefficients again, we can see that we get, again, the same value that we were getting, mean difference in length, comparing men to women at baseline. Sorry. For age, we also get the same value, mean growth in 1 year. And then for the interaction, adding these two coefficients, we also get the same value. So what's this telling us? Is it worth to fit the random intercepts and random source model? Not really, because we're getting the same results. So we should go for the simplest model.
But this is just saying that there's not actually a difference in slopes.
Not a statistically significant one.
Okay.
Although, you could also look at the random effects, but normally people are not interested in that. We just fit random effects to account for the correlation structure, but the estimates we're interested in are the fixed effects, right, to interpret them. So, yeah. Also, I mean, the sample size here is 26, so maybe it's like you might get some different results if you had a higher sample size. So it's not telling you that there are no differences, it's just the statistical, there's no statistical significance. So there's no evidence to affirm that with the data you have. Now, what you were all waiting for, let's compare mixed effects to GEE. So mixed effects in GEE should be equivalent for continuous outcomes, right? But the main difference of these two models is that one of them is marginal and the other one is conditional. So how does that matter if they are equivalent? Well, it matters especially for outcomes that are not continuous, and we'll go through that in a minute. So, but let's first compare, because mixed effects in GEE might have equivalent interpretation with continuous outcomes, but they have some specific features that are not common, those two models. So for mixed effects, a good thing that they have is that they can handle small numbers of clusters and multiple levels of clustering pretty easily. The syntax is quite straightforward, so you can actually do some nested clustering there. They might also be more intuitive, although this is a personal choice, but people are really used to fitting in linear models. And the math behind GEE is much more complex than using, linear models and this kind of terminology. That's why I didn't put any equation in GEE, because I didn't want you guys to get super confused. But in terms of the mathematical development, it might be more complex. But again, in terms of estimation, that's just a preference. So a feature of the mixed effects models is that normally you assume equal correlation between individuals in the same cluster. And you might be able to modify that, but that's more complicated as compared to GEE, which you're actually able to specify the correlation structure you want to. So for example, for longitudinal models, which we assume that there's equal correlation, people just can use mixed models with any further specification, and that's an easy job. And then a very important thing, that's sometimes why people choose mixed effects above GE, is that they can handle balance as well as imbalance or missing within subject data. So that's more difficult in GEE. In fact, GEE, one of the best things that this model has is that it provides consistent estimates and valid standard errors, even if the correlation structure is misspecified. And actually something that's really cool, as I showed, is that you can actually see how correct you were about the correlation structure you were fitting, because you can compare the robust standard errors to the calculated with the sandwich method to the standard errors that were fitted using weighted least squares with the correlation structure that you specified yourself. So you are able to evaluate that, but again, even if you're wrong, the estimate should be correct. So some drawback is that you cannot easily accommodate complex clustering designs. So using GEE for nested clustering, for example, different clusters of different hospitals and different repeated measures within the same hospital and so on, those different levels of clustering are much more difficult to account for in GEE. Is there a question?
Someone says, I want to assess longitudinal effect of air pollution on health outcome. Air pollution is postal code level. I want to use GEE as my target. It says to estimate population level effect. However, I do not see in the literature many uses of GEE compared to mixed effects. Is there any caveats or problem of using GEE in environmental epidemiology? I found it useful as I can also use user-defined spatial correlation to be tested.
Okay, so first of all, I assume that the air pollution measurements are not repeated, because I'll go through this now, but if you have repeated measures on the exposure, that's a different problem and much more complex, but we'll go through that in a bit. Regarding the question, GEE is perfectly fine for environmental data, just as mixed effects models are. I know that many people prefer to use mixed effects models because it's just simpler. Again, people are used to using the LM command in R and obtaining the output and so on. So this is just an extension of that. So it might be more intuitive to use mixed effects models, but GE is perfectly fine. And you're totally right that with GE, you can specify spatial correlations your own correlation structure, that's something really difficult in mixed effects models. So for your setting, I agree that using GEE is a reasonable choice. The reason that you don't see GEE that much is just because people might consider it more difficult, and that's why it's less popular. Also, a problem of GEE is that it's not robust to data missing at random. So that might be a problem that you might also need to consider. But if you want to specify those complex correlations, then, I agree that GEE is a really good model. I don't know if they are following up. I don't know. Okay, great. Yeah, so as I just mentioned, GEE requires sometimes larger sample sizes and is not robust to data missing at random. So that might be a problem because sometimes, you do have imbalanced clusters. So it's very common that some people have 5 repeated measures, others have like 4 or 3, So mixed effect models account for that really well. And it's not that straightforward in GEE. Also, as I said, it's quite unclear how to perform model selection because even if you can use QIC, some people are advising against that. So again, it's not a likelihood-based model, so model selection might be a little bit more tricky. Yes, Kate?
So if the correlation within a subject or within a cluster is really low, then it may not be useful to use a longitudinal model.
Yeah,
But
so
how would I assess which would be the better way? I mean,
so you can actually compare a mixed effects model, for example, with exchangeable correlation, which assumes that the data are correlated, to a regular linear model. If the results you obtain are the same, then that means you don't need a mixed effects model. And that's actually important because mixed effects model are an additional complication. That's why I was comparing it to adjusting for confounding. So if you just obtain similar point estimates and standard errors when using linear models and using mixed effects, and it's not worth it, And that might happen because you don't really know the underlying correlation structure of your data. You just assume, but you're not sure. So it's worth also comparing it to a simpler model. So I'm gonna go through some final remarks that are relevant. So again, for continuous outcomes, the population average and the conditional models are equivalent. So results for mixed effects models and GEE should be equivalent as we just saw in this example. This is not the case for generalized mixed models. And the reason is that for generalized mixed models, such as, you have a link function, for example, a Poisson link for Poisson regression, a logit link for logistic regression. So that link makes it not comparable, taking the mean, the average across the population, or having conditional effects. So they might not be equivalent. So that's where you need to be more careful regarding interpretation of marginal and conditional effects. But again, for linear models, you should be fine. Then another consideration is that this is a very common question, actually. Mixed effects models in GEE should not be used in general when we have clustered outcomes and exposure, only for clustered outcomes. So keep in mind that random slopes and random intercepts only apply to the outcome, not to the exposure. So some people are, for example, asking, well, I have a repeatedly measured exposure over time and an outcome. That's not the way you should use mixed effects models because the interpretation is very tricky there. So this is an additional layer of complexity. And for cluster exposures and outcomes, we should either use the parametric D formula if we're interested in causal inference. So that's a valid way to estimate, to account for time varying confounding, for example, in time varying exposures, or models that are more complicated distributed lag models, observation varying coefficient kernel machine regression, but not mixed models. All right, thank you so much. So I see there are some, I think, other questions in the chat. So happy to answer them. Do we have time? And then, oh no, okay, great.
I thought you could use a mixed model if you have a clustered exposure and a clustered outcome.
So the problem with that is the interpretation is really tricky,
Okay.
So it's not the best way to go. If you wanna have an interpretable model, you should use instead these methods like the G formula and distributed lag models, because here we're modeling the association between a predictor and the longitudinal change. But if your predictor is also longitudinally changing, then it's not really clear how that will translate into an interpretation.
I have a question. So if we have multi-level data, but we don't have repeated measures within an individual, can we use GE or linear mixed effects or just mixed effects?
Yeah, absolutely. So any clustering level you have, you can use the or mixed effects models. So the clustering structure is different. If you have repeated measures, your clustering variable, your clustering structure is the individual. So you have repeated measures within individual. Each individual is a cluster. Whereas, for example, if you have cluster data, like spatially or in hospital or in schools, that's very common, like kids in different schools that are subject to different interventions. So there, the clustering structure is not the individual anymore, it's the school. So you have several individuals in one school. In longitudinal data, you have several measurements in one individual. So what changes is your clustering structure. But you will definitely be able to fit both GE and mixed effects models with any clustering structure you might have. You just have to take care of how you specify for example, the random intercept. So in that case, the random intercept will not be the ID, like the individual, it will be the school or the hospital.
Okay, thank you.
Yeah, so I mean, doing that in GE.
Like we take the example of school and individual.
So doing that in GE is super complicated, but in mixed effects models, with this specification you have, like age ID, you can actually modify like here. Yeah, here. So this random part allows actually a lot of flexibility in terms of nesting. I can show you later some code, some specific code for nesting, but there you can actually treat multiple levels fixing for the random effects. So you can even have like nested levels in random slope and so on. So that's easier to do. Whereas for GE, it's not super clear. So for like these multiple level clustering, mixed effects models would be more straightforward. So I can see what.
Could you repeat what you were saying about using the maximum likelihood versus the restricted maximum likelihood?
Absolutely.
Like when is that best?
So, all right. So the only problem with maximum likelihood is that when the sample size is small, it might be biased, but also here, again, we not only have the parameters of the regression model, we also have some additional uncertainty associated to the random effects. So restricted maximum likelihood takes into account in the degrees of freedom that we have those additional parameters. And it's used to estimate the variance in settings of small samples. But, so there are two things about this. Normally the default is restricted maximum likelihood because when the sample size is big enough, they should be equivalent, maximum likelihood and restricted maximum likelihood. It's just that if the sample size is small, they might not be equivalent. However, for model selection, this is for model fitting, like for estimation. If you want to select between nested models, then that might be a problem. So some people want to select between a model with the same fixed effects, but with different random effects. That might be okay with restricted maximum likelihood, but if the fixed effects are different between those two models, then that might represent a problem because it's not super clear how to account to the fact that they have different degrees of freedom and so on. So for model selection, I think the easiest thing would be to use maximum likelihood if you want to just compare the two models. But then for fitting, restricted maximum likelihood would be you just assure that you are doing it. All right, I think we don't have any time left, but so please feel free to contact me via email. I will share the slides with all of you, and feel free if you have questions to reach out to me. I hope this was useful for you all and you learn a little bit more about how to fit longitudinal and cluster data models. Again, this was not a super advanced workshop, but hopefully it helped a little bit to set the topic. So thank you all so much for being here. I can't look at the comments, but thank you.
So clear.
But what's going on? Are they just saying thank you with me?
Yeah.
Okay,
Thank you.
great.